Hello and welcome to the fifth in a series of lectures covering Chapter 18. Today we'll be talking about longitudinal waves in air columns. Before we do that, I just want to do a little intermission of sorts to establish that standing waves can also exist in longitudinal form. That is to say, you can have a sound wave superposition that creates a standing wave, or in the case of the GIF shown here, we have a spring that's creating not just a longitudinal wave, but a standing longitudinal wave. So you can note, particularly in the last three rows, that the spring seems to compress and expand at different nodes, but you can't really see the wave move, and that's because what's actually happening is that there's a superposition of a wave being sent to the right and one being sent to the left continuously, and this results in these points of max stretch and compression, like a constant accordion throughout the whole slinky. So if we were to show this where the pressure density is graphed on a vertical axis as a function of the position through the string, then we know that there's this pressure nodes, points where the pressure is constant, it doesn't change throughout the whole cycle. And these points, occur at fixed points throughout the spring, since this is a standing wave after all, so the nodes remain where they are, and the number of nodes that you have is determined by which normal frequency or fundamental frequency the longitudinal wave is oscillating at. But then there's this point where the spring reaches as much compression as a sort of big sandwiching of all the nearby loops in the spring. So again, because it's a standing wave, these points happen at fixed intervals. And you'll note then that when it comes to then the compression of the medium, right, this are compression antinodes, because nowhere else on the medium does the spring compress as much as it does here. Now, in the in-between areas between the nodes and the antinodes, right, you see that the medium does stretch a bit and compress a bit, but there's this like full compression on the antinodes. And if you kind of hover your finger over a node, you'll see that the loops of the spring don't really get wedged in at this node points. The sort of part of the spring that belongs to this node right here is always kind of moving left and right, but never really gets sandwiched, right? It helps sandwich the antinodes to the left and the right, but never quite the point it is at equilibrium. Now, if we were to graph the displacement of each piece of the spring as a function of its position, then where we had pressure nodes, we actually have displacement antinodes, because this point right here, for example, at the very beginning of the spring, this is a pressure antinode, since the whole kind of rings here kind of get pushed to the right, creating this maximum pressure point right over here, which means that at the starting point, there's, no pressure change. Everything kind of gets shoved over here. But when it comes to the displacement of this point, then this is a displacement antinode, since this part of the spring is displacing as much as possible to the right. And so if you can kind of see this area right here being a displacement antinode, as you kind of move towards the first displacement node, you'll note that each kind of little loop of the spring displaces less and less until you reach the displacement antinode here, where you kind of see, right, this loop right here is barely moving. It's getting kind of wedged between the loops on the left and the right, but it itself is not moving all that much. But if you look at the next antinode, right, this bit of spring here is constantly moving left and right from its equilibrium position. So pressure nodes are displacement antinodes and vice versa. You put them side by side, right? They are both describing, again, the same spring, the same standing wave. It's just that you can use either a description of the wave in terms of density or displacement to describe a longitudinal wave. Although we've seen that the pressure density is sort of something that makes a wave. It's a very particular property of a wave that is like constant change in pressure through the medium. So we're more likely to talk about longitudinal waves in this sort of pressure density picture, especially since when it comes to sound waves, right, moving through gas, it's more logical to talk about the pressure changes in gas than necessarily displacement of the air molecules. So in the same way that we saw standing waves and strings that are fixed on both ends, we can look at boundary conditions for longitudinal waves, particularly sound waves in air columns. So for example, a pipe organ, right? The giant pipes kind of have air coming in one end and out the other, or even a clarinet where you blow air through one end and you have a note that comes out the other. And well, what that happens is, right, the note that you hear is resonance that occurs as air blows through those pipes. There's this kind of sound wave that flows through and it harmonizes with the instrument, and so there's this resonance where the natural harmonics of the instrument are heard the loudest whenever you blow into them. Or same actually, if you blow into a bottle, that's also a boundary condition, since you have an open end where you blow into the bottle and there's like a closed end at the bottom of the bottle. So if you blow into a bottle and you have your lips pretty close to it, right, you hear this like particular loud pitch, even though you're just blowing into it, right? You put the bottle away, right? You blow into the air, you just hear yourself blowing air. But when you do it next to a bottle, you hear this sound, and that's because part of the sort of wave that you're releasing of air into the bottle resonates with the natural harmonic of the bottle, and that resonance kind of makes that particular note that you hear when you blow into the bottle sound a lot louder than just if you're just blowing into open air. So in the case of a pipe organ, it's kind of like a bottle where you have this like huge pipe and sound waves, air just basically oscillating through the pipe. The boundary condition for a pipe organ would be that on one end, the end is closed, and for the displacement of medium, since this is the closed end, the medium at that point, it has nowhere to go. It kind of gets wedged in the end. So it's kind of like the end of a string that's right next to a wall. It can't move anywhere. So this is a displacement node. It's a area, right? See, it's the bottom of the bottle. It's the end of the pipe organ. Air particles have nowhere left to travel. And if you are describing the sound wave, though, in terms of pressure, then the closed end of a pipe as actually a pressure antinode, a point of maximum pressure variation, because all the pressure gets kind of sandwiched at this point. And when it comes to the open air end of a column, so the open end of a bottle, the other end of a pipe organ, these are approximately displacement antinodes and equivalently a pressure node. The reason why it's approximately is because essentially at the open end of an air column, that end is in equilibrium with the pressure in the atmosphere, and that's constant, right? So the pressure really isn't changing at the open end, so it's a pressure node. There's no change in pressure. But it does mean, though, that the medium over there kind of, still squish the particles further down the pipe, creating a displacement antinode. But we say that's approximately because this sort of open end air, this sort of boundary between the end of the pipe, the open end of the pipe, and the atmosphere isn't so strictly defined at the very end of the pipe. It actually kind of happens roughly a little bit away from the open end. And just in case it wasn't clear, though, again, standing waves are occurring in these in organs, in clarinets. Music's being produced from these standing waves of sound, because what ends up happening is that, right, you're blowing into a clarinet, or there's air blowing into a pipe organ. Then you end up with this sound waves that are traveling back and forth through the pipes, and then they create a interference pattern. They create a standing wave, and in the case of instruments, right, those standing waves are the harmonics of the instrument. So again, at the open end, there's no pressure variation because it's in contact with the atmosphere, and you can kind of think of this as analogous of the wave on a string reaching a open end and then getting reflected back. So that's kind of what happens with a sound wave. The open end of a pipe acts as a boundary which reflects the wave back, and that's how, right, standing waves are set up, right? Because you have a wave coming in, gets reflected back, and the superposition creates standing waves. So that's what's happening at both the open and the closed ends. Although it might make more sense to imagine than that a sound wave moving into the closed end of a pipe gets reflected back. It also gets reflected back when it reaches the open end. Um, and part of the reason is because even though beyond the open end, even though the medium's not changing, it's not like a wave on a string that reaches a wall, which is entirely new medium. When a sound wave reaches the open end, right, there's just air beyond that end. So while the medium's not different, though, the sort of character of the medium, of the open air versus the pipe, is different enough that the atmosphere acts as a wall to the wave, which reflects it back into the pipe. So if you have a pipe that's open at both ends, then what you actually have is a wave that's similar to the displacement condition. And I'm just realizing now that the pictures for these waves are actually flipped. So the picture for a pipe open at one end should be this one, and the one for the close to one end should be this one. So a little fix here. Don't mind that. Bob Ross used to say, there's no mistakes, just happy little accidents. So exactly what we're seeing here. So when you have a sound wave traveling through a pipe open at both ends, it gets reflected and creates a standing wave. And the boundary conditions in this case is that the pipe being open both ends means that both ends must be um, displacement antinodes and pressure nodes. In other words, both ends of the pipe are points where there's no change in pressure. So the first fundamental frequency is one where there's only a single pressure antinode in the center, which is the same as saying that there's a displacement node in the center. So basically, the particles all kind of get sandwiched in the middle and then kind of swing back left and right and then get sandwiched again cyclically. And so this boundary condition means that the wavelength of the standing wave must be some integer division, must be two times the length of the pipe divided by the wavelength. Sorry, divided by n, where n is the harmonic number. So lambda n is equal to 2L divided by n, which is the same limitation on harmonic wavelengths that we've seen for a string fixed on both ends. And so the harmonic frequencies actually have the same formula as the harmonic frequencies for a string on both ends, which is the harmonic number n times the speed, in this case, the speed of sound, divided by 2 times the length of the pipe. So the graphs here, right, they're showing you displacement as a sort of function on a y-axis, even though the actual displacement of the particles is happening left to right along the sort of same direction as the waves propagate. But it's just kind of showing you how, like, most of the displacement happens here where the medium kind of gets shoved to the right, but no displacement happens here. The air particles at this point don't really move that much, but they get wedged in left and right, which is why it creates the pressure antinode. And again, right, so in the first harmonic, only half a wavelength fits the entire pipe, and for the second harmonic, an entire wavelength fits, and then for the third harmonic, wavelength and a half. And then as the wavelength decreases for each harmonic, the frequency increases by a factor of n. So for the pipes closed at one end, the closed end, right, the particles can't move, so it's a displacement node. They're just going to get wedged in by other particles right behind it. So you end up with this pressure antinode, which is also a displacement node since particles are not moving. So there's an open end on the left, which is an antinode, and it's a node for pressure since, again, this end right here is in contact with the atmosphere, so its pressure is not changing. And so the boundary condition in this case is that on one end must be a displacement antinode or pressure node, and the other end, the closed end, must be a displacement node or a pressure antinode. Either way you look at it, the condition is that you need a node on one end and an antinode on the other. You might recall, and this still holds true for longitudinal waves, that when we talked about transverse standing waves, a node and the neighboring antinode are a quarter of a wavelength away. With a bit of math, then you can figure out that in order to satisfy this boundary condition, the first harmonic must have 4 times the length of the pipe as its wavelength. And this ensures that you'll have a node and an antinode at either end, respectively. So the fundamental frequency then is a bit trickier to figure out because it's an odd multiple of the speed of sound divided by 4 times the length of the pipe. Or you can also, there's another way to find it out where you have 2n minus 1 as your sort of harmonic number, where n can go anywhere from 1, 2, 3, and beyond, times the speed of sound divided by 4 times the length. And this still means that the frequency is still incrementing, as a multiple of an integer, but now it's an odd integer. So standing waves is the reason why wind instruments make sound, or brass instruments make sounds, as blowing into them generates resonance in them. So imagine what happens to frequencies of instruments, just based on air columns, and well, even strings too, right? Because we saw how strings can also create resonance. And it's interesting to think about the chamber orchestra. And funnily enough, if the temperature is rising in the room, then the sound that's coming off the flutes actually becomes sharper, because there's sort of like an increase in the frequency of the sound and increase in the pitch, because as the flute warms up, because as things get hotter, the speed of sound increases, and so that leads to higher frequencies. But for a string instrument like the violin, then as the room gets hotter, then the strings are kind of thermally expanding, which causes the tension on them to decrease. Now, amount of thermal expansion that the string undergoes, right, from like a 1 degree temperature isn't that much, but it is enough to create a small shift in frequency, which to a trained professional, somebody who's really, worked their years off in music theory and playing instrument and composition, they could really tell apart. And of course, marching bands are a great example of percussion and harmony, since you're mixing the beating of drums, which doesn't necessarily create harmonic sounds, but it does create a good backing soundtrack to the harmonic and melodic instruments. So the way that woodwind instruments work is that there's this kind of like rich sound that comes by the harmonic vibrations of a reed. If you got like a brass instrument, then that's essentially just, like the saxophone or the oh boy, I'm forgetting my jazz instruments, or like the tuba, right? Where like there's the vibration in the player's lips that are blowing into the instruments. That's where the sound comes from. The excitation of air, of waves, are coming off the tube by the vibration of the player's lips. Or similar with a flute, right? The excitation, the harmonizing that happens in the pipe of air comes from blowing over the edge at the mouthpiece of the instrument. And the flute really then works similarly to blowing across the opening of a bottle, with like one of those narrow necks. And like I said, just blowing air as it rushes into the open bottle. There's a lot of frequencies to the air that you blow. You can't even tell them apart. It just sounds like blowing air to you. But when you do it into a bottle, it sets it into resonance, and you get that cool sound. So a pipe open at both ends resonates this fundamental frequency F open. So right now we're switching into a quick quiz before the end of the lecture. And we know the frequency of the open pipe. And then we're saying that, okay, one end is covered and the pipe is made to resonate. And so there's this sort of other fundamental frequency that we define, since after all, when we cover the pipe, we are changing the boundary conditions. So which of the following expression describes how these two resonant frequencies compare? So we're comparing the resonant frequency of a pipe open at both ends versus one that's closed at both ends. Sorry, that's closed at one end and open at the other. If you recall, the pipe that's open at both ends has either an antinode on either end, if you're looking at the displacement of the medium, or it has a node on either end if you're looking at the pressure variation of the medium. Either way, because these are two nodes, it means that they are a half wavelength away from each other at the fundamental frequency. For the pipe that's close on one end, there's a node and an antinode, so they're a quarter wavelength away. Sorry, they are a quarter wavelength away compared to the one that's open at both ends. That must be, the boundaries are a half wavelength away. So the difference is a half. The fundamental frequency of the closed end one is half of that of the open end, because the fundamental frequency of one that's open on both ends is able to fit a half wavelength, while the fundamental frequency where there is one closed end can only fit a quarter wavelength. And so that's between a quarter and a half, that's half the frequency. So this second quick quiz question is asking about Balboa Park, and that's San Diego, where they play baseball. There's a nice big outdoor organ. And the question is, well, as the air temperature increases, what happens to the fundamental frequency of the organ pipes? So the fundamental frequency, if you recall, is essentially a function of the length of the tubes of the pipes in the organ and the speed of sound in air. If the temperature increases, then you'd expect that the fundamental frequency increases as well. So fundamental frequency goes up, and so does every harmonic frequency.